Check, check. So yeah, it's two of us at the moment. Although yeah, I'm streaming this as usual, so we'll see if people have questions online. But let me know if you have anything in particular. So I was gonna finish off on the stacking. Did you? I know you were working on the assignment. Did you get? Are you done with the stacking already, or are you still working on it? Have you finished all the next assignment on ensembles yet, or?
Starting to say started.
Yeah, did you? Okay. Okay. But yeah, I was gonna give a few more details on the stacking part, and then yeah, I might jump also to talk a little bit about unsupervised learning, or at least begin talking about that. So anyway, sure, this is all working here. So yeah, so don't forget to make sure you have the assignment submitted by tomorrow. So I'm going to finish up talking about a few things on that here today. We've got just one more week of face-to-face classes, but then a finals week as well. But I might start talking a little bit about unsupervised learning today as well. At least introduce it. So we still have one more assignment 7 on unsupervised learning, principal component analysis, stuff like that, and a test. And of course, also don't forget your class projects again. So just remind people about all those things. So we can talk more about the test or other stuff today or next week. But yeah, the test should be the same format. So hopefully everybody's familiar with that. And I'll have that open up for quite a bit of time starting at the end of next week and give you about a week to be able to take the second test. So all right, so I'm just going to finish up with a few things about ensemble learning. I wanted to bring up the textbook real quick because a couple of things that I had maybe skipped over that I wanted to mention, especially about the bagging and the pasting. Yeah, I didn't really talk about out of bag evaluation, and also I was only hinting at a little bit of the idea of sampling the inputs versus sampling the features. So the textbook actually, if you read it, uses these terms of patches and subspaces to come up with those ideas. So so in our lecture notebook, we did mention a little bit about like feature importance. So one thing that you can use random forest for the out of bag evaluation and the feature importance when we were talking about bagging and pasting here. But I didn't really talk about those any on Tuesday, last time we met. So just to review a little bit of some of those things. So, random forests, random forests and extra trees are a good method to know, to use. They work surprisingly well, given that they're relatively simple. They're just a collection of a bunch of basic decision trees, which we, talked about last week a bit. So the tree, there's a couple of advantages of these that I didn't talk about. So for one thing is that they can scale really well. So these can work really well when you're working with a big like clustered computer. So you can parallelize them. Because basically each individual decision tree and like a random forest or a extra random set of trees can be trained pretty much, independent of any of the others. So you get perfect parallelism. So if you have a large number of CPU cores, or even if you have like a distributed computing system, you can make big random forests relatively efficiently in in this way. So, the general technique, we're talking about sampling here. And we did mention bagging and pasting, like the textbook hints at. If you read through this, I guess that another name for bagging is this bagging is just short for the bootstrap aggregation. So the parameter, if you want to use either bootstrapping or not bootstrapping, you would select a particular parameter in the bagging classifier. So there'll be like a bootstrap parameter that you set as true or false. Just want to have like an example of it in here. The difference being, according to the textbook, that if you use the bootstrapping, which just means that you're doing sampling without replacement, apparently that usually works as well, if not a little bit better, than just using sampling without replacement. So I wouldn't be able to tell you exactly why that's the case. So the default, I believe, is just to use the bagging or the bootstrapping. But you can turn that off by setting the bootstrap to be false. So you can always check whether the one or the other works better. So, but for both of these, at the beginning of this, like we started talking about, we're talking about sampling the feature. So if we're training to using like a decision tree classifier, where we're going to build 500 separate decision trees. The default is when we fit with some training data, it will sample some number of inputs or samples from the input training data, right? And again, that's another thing you can specify, the max samples when we're doing the sampling here. This is going to be either doing with or without without the bootstrapping here, depending on how you set that. And for some of the reasons that we talked about, this tends to work surprisingly well, right? So even though we have a bunch of decision trees that are built just using small samples of the input training data, when you aggregate those together, they'll have seen different parts of the data, so the aggregate will tend to perform surprisingly well in terms of being a classifier overall to make predictions on unseen data, right? To be able to generalize. Like they said, technically in here, the ensemble has a comparable bias, but a smaller variance. Which kind of means that you tend to get smoother decision boundaries when you're using an aggregate like this. Okay. So some stuff that we didn't talk about. So another kind of thing that's nice that a lot of people use random forest for is to do estimates. I guess I'm skipping ahead here. So do estimates on feature importance. But another thing that you can do, you can also, this out-of-bag evaluation, if we didn't talk about it, or if we didn't read about it, can also give you an estimate of how well the ensemble is going to perform without splitting into training and test data sets. Okay? So the basic idea on this is, remember, when we create each individual estimator on the ensemble, they are just trained with a subset, could typically be a relatively small subset of the training data. So that means that you can actually validate, without having like a separate validation or test set, you can, in theory, evaluate the individual estimators on the data, on the full data set, or on the feature, or on the samples that they didn't see. Okay? So anyway, so that's really what the out of bag is referring to. So so overall, if there were some samples or inputs that weren't used, those remaining ones are referred to as the out of bag instances, and there are things that are built into these kinds of ensembles. Well, the bagging classifier in particular, but I think it can do that. The same thing with like the random forest nearest trees will allow you to do this out of bag evaluation here. But yeah, the way, and I might have asked you guys to do this on the current assignment. I can't remember if I asked you to report the out of bag evaluation or not. So, but this gives you a similar measurement of how well you can expect your classifier to generalize without necessarily having to split off a separate validation test set. So yeah, like it's shown here. It won't be always the same, but it gives you a feel. Bag score ought to be similar to what you might see on unseen test data. Although it's pretty far off here, 92% versus about 9%. Okay, so also we touched on this last time as well, but yeah, I didn't mention the idea of the patches and subspaces that the textbook talked about. The default for kind of ensembling decision trees like this for bagging, this is really a general method. You can, in theory, ensemble any kind of estimator, but decision trees are kind of the easy one to do, the straightforward one to do. But besides sampling from the inputs, the rows of your data set, you can also sample the features. And sometimes that can help as well in terms of increasing the variety of the estimators that you end up with on your ensemble, which can likewise then help with your performance. So again, all these things depend on the data set that you're working with, whether they're going to give you much of a boost, if any, or not. But sometimes they can. So yeah, I guess some people call that doing patches when you're sampling. They call subspaces when you're sampling on the features. And in theory, you could sample both training instances and features. And according to our textbooks, some people would call that taking random patches. So that's taking samples of even smaller. I guess the idea is you're just taking a patch of the full matrix, both some number of inputs and some number of features. You do both at the same time. All those, if you understand the ideas of bias and variance, mostly these are playing with, you're going to be increasing diversity, but you'll end up lowering variance, or vice versa, stuff like this. So also, I did want to mention the feature importance. Recommend people don't kind of skip over this part as well. So another kind of thing that you might want to be doing when you're doing data exploration, before you start building your models is, so when you're looking at the features of your data set, you you usually want to get a feel for which features are going to be more important and which are going to be less important. And maybe even find, so when you do things like check the amount of correlation between features, you might uncover things like some features are really highly correlated or perfectly correlated, which means that they're really just the same thing. They won't really help you if you have both of them, right? So one reason that, like we've done before, where we ask you to look at how correlated features were with the thing you're trying to predict, but also how correlated features were with each other, is that things that are highly correlated with what you're trying to predict are likely going to be important when you make models. When they're low, when they have a lower correlation, they're less likely to be useful. Likewise, if features are highly correlated with each other, they might be able to be dropped or combined in order to use less data, which can help build bigger models, or at least build them faster. So besides doing straightforward correlation, there's many other methods for doing some exploration on your features and how they might work or help with your model. So one of these is in a simple like forest ensemble. So for decision tree ensemble, so for a random forest, the basic idea on this is that since we're sampling like our inputs, usually generally, if you look at where in the tree a feature ended up being selected to be used, so because of the way decision trees are built with the cart algorithm that we talked about, the one at the root, the one at the very top, is the one that's going to give you the highest separation. So it gives us the biggest gain in your measure of the Gini score or whatever you're using. So that feature that results in that is, in some sense, the most important one. Right? And then the ones on the next level of the tree are going to be kind of second most important, and so on. So where they first appear, or how often they appear in the tree, and how high up. And the decision tree is a measure of how useful that feature is for doing classification, for classifying the data set. So when you're working with an ensemble, a random forest, you have lots of trees. So you can combine that overall. So make a measurement of for each of the features, how often it was at the top node or the second level of the tree, or so on. So yeah, for random forest, probably for extra tree as well, it gives this to you automatically. This way of measuring the importance of features by where they appear on the different decision trees you have. So you just have this feature importances member variable for your random forest classifier. So it should give you a number. It should add up to 1 because it ends up being kind of like a probability space. Importance is here, so 6. So, yeah, probably, basically. So anyway, the higher the number, the more often it was as like the first or at the top of the tree. The lower the number, the lower it down, where it appeared or first appeared for making decisions. So by that, it again, using the iris data set, we're getting the petal length and petal width are much more important than the sepal, the other two sepal features on this iris data set. Yeah, I don't remember if I had these examples in the oh yeah, so we did recreate those on there. So as another example, this shouldn't be too surprising, but again, using the feature importance on the MNIST data set, which we haven't talked a whole lot about. I know we've looked at it once or twice in this class before. So, but this shouldn't be surprising in that here, since every input on the MNIST are digits, all the important pixels are going to be pretty much like kind of in the center, where since the images were centered and so all the drawings end up in there. So you end up with these pixels here, where usually you had the actual digits as highly important, and of course the stuff around the edges you don't really need because usually there's not an actual pixel in there, so there'll be low or no importance in terms of building like a classifier. Okay. Okay. So let me just move on to stacking. I'm going to skip over boosting, although I was going to mention that yeah, I noticed that this notebook wasn't running. So I'm trying to remember. You probably have to install just that this has changed since last time. So yeah, it's saying that the algorithm features. Yeah, so here we're takes a little bit of time to fit the MNIST data set in random forest here in order to do this example for the feature importance. So yeah, so I guess I just hadn't checked this notebook. So apparently something's changed in the Ada Boost classifier. It doesn't support the algorithm anymore. So I guess if you just remove that, you should be able to do the example there. This notebook. I don't know what happened to that. Okay, so let me jump then to talk a little bit about stacking. Just a little bit more details on this for anybody that's maybe still working on this last part here. There wasn't a whole lot in the lecture notebook from this section because there wasn't a lot of example code on here. But just to make certain that everybody kind of understands what we're doing here, I kind of want to open up the assignment as well here. So go ahead and open up our assignment 6. So yeah, the assignment 6, it really starts with task 5, where you start by building some methods. The purpose of the create stacked data is to set this up so that we can have input data set that we need for this stacking classifier. So and then you end up reusing this one for the methods for the next part here. So so yeah, anyway, let me just jump back to this. So I mean, what you're only doing in the task 5 and 6 is reusing some of the stuff done in the previous tasks. So you're going to be using the same kind of 5 classifiers. So that's part of the thing that you should be reusing on those. But then you'll use the different estimators for the first layer of a stacked ensemble. So you have to actually train those on the training data and then run the validation data through those to get the outputs. And then the outputs of each one of those we end up stacking together. That's what the method in the task 5 is supposed to be doing, to be used as input to create a final estimator. And so So yeah, we did ask you to use a support vector classifier as the final classifier there. I mean, in theory, you could have done any kind of classifier that you wanted to try out there. So we are asking on the task 5 function that you use the prediction, the probability predictions from each of those. So since this is a binary classifier in this task, each one of the 5 should be outputting, a probability for the yes and the no, the true and the false for the data set. So we're still using the same data set for all this assignment here. So So if we have 5 classifiers, which when we stack those together, we're going to have 5,000 output, but we're going to have 5,000 samples, but each one of them has 2 output features. Probability, its estimate that it was the yes, and its estimate that it was the no on this magic telescope data set. So basically, the result of stacking these together should be that we end up with 10 columns. 2 for each 5 estimates that we have. So I mean, that's really what's kind of. I mean, another way we could have done this is to just use the final prediction. In theory, if you're using the confidence or the probabilities, you're getting a little bit more information, so you can build a better blending ensemble here. You can, so one first thing that you can do with these is just take the output, the predicted output. Whether in this case, since we're using a classification, would have been just 0 or 1. Right? So in that case, it would have only been 5 outputs, what the final prediction was for each of the classifiers at the base level. Here, if you read through, I think it's talked a little bit of like a regression problem in the example. So, instead of predicting, some class 0 or 1, we have something where it's predicting a real value. But so you can do this both for regression or a classification. It's kind of stacking ensemble here. So yeah, I'd forgotten. I hadn't realized there is actually a stacking classifier. I think when I made this assignment, they maybe didn't have that actually in scikit-learn, so we kind of build this by hand. But so in the most recent versions of scikit-learn, I guess there is sort of like the ensemble classifier. There is a stacking classifier class that you can use to build up within the API. So, but yeah, we are doing it by hand, but we should end up with a similar result as what would happen if you use the stacking classifier from scikit-learn. Another thing, I mentioned, you can also extend this idea, so you could have multiple levels, so you're beginning to build up something that looks like a neural network if you did something like this. So have one layer of estimators, and those go into another layer, and so on. Usually, I don't think usually unlikely, unless there's some specific reason, you're going to get much of improvement by going more than just a single level like this. Okay. So yeah, so I think I think that couldn't think of anything else I wanted to bring up on this. So let me know if anybody had they're stuck on these or any questions on the stacking ensemble. So yeah, once you build this, so you should be reusing your the 2 functions from before when you do the final one. Create stack data. You do need to be careful that you're using the training data to build the voting ensemble, and this should be reusing the methods from the previous tasks here, and then your final blending estimator. So 2 things are actually getting returned from this. So the final estimator, which supposedly should have been a support vector classifier, should be trained on the stack data that comes from the voting ensemble, and you use the validation data. When we evaluate it. Okay. I guess we did ask you to plot the confusion matrix, and actually also the ROC curve on this. So since this is a binary classification, some of the stuff that we talked about for evaluating how well classifier is doing. You can use those same methods to evaluate here. I don't remember if we asked to do ROC. I guess we did. So in general, you have to go back and remember those plotting ROC curves. We asked for those in a couple of different places. All right. I think. Okay. Yes, I had some questions. Yeah, the for reproducibility on these. Let me check the tests here. So when we're testing your methods on these, like for test 6, we are reusing your method to split up into 3 the train, validation, and test data sets. So for there, if I remember right, you were supposed to be we were supposed to so yeah, I mean, we set the seed before we call your function there, so I don't think you had to do anything specific with setting a seed to get the same split for the initial splitting into training, validation, and test data. But yeah, otherwise, I don't think that there was anything specific that you had to do to ensure that we weren't getting different results on random seeds and things. Let me check here just real quick. So yeah, actually, so I might have to check a little bit further on that, but I believe that yeah, really there wasn't. You should be able to pass the tests without having to explicitly set seeds. I think for most all this stuff. So we're not really testing that detailed results here. We're mostly testing that you get basically like scores above particular levels and things like that. Yeah, so you should for like the task 5 and 6 stuff. There are some places where you probably just should have a loop in there, so you won't want to try it. You probably can't really vectorize it, so you'll have to loop through like the 5 estimators that you have when you're doing the things on the task 5 tasks. So, to get these all stacked together. You don't have to vectorize the task 5 one in particular. Probably be a lot more straightforward to just make a loop through each one and somehow build up. So there's different methods, of course, you can use to build up a NumPy array, which is what should be being returned from this, but you can do those inside of a loop. Okay. Yeah, I'll check on that. Yeah, I can't quite remember, but yeah, I'll check a little bit more details on the randomization. But yeah, I don't think that was really an issue on this assignment. So just because looking at the test, we're not really doing anything real specific on expected results coming back out of it. But I have to check on that in a little bit more detail. Okay. So I have a little bit more time. I'm just going to um, mention a few things about. So next week we are starting on kind of a new topic, unsupervised learning. I'll just bring up the textbook, don't I? So we are looking at really chapter 8 and 9. But again, we kind of ran into some. My schedule was a bit compressed because we started a little bit late. So sorry about that. I mean, I'll talk more details about these two chapters next week. So the next assignment, I would encourage you to finish up the current assignment and maybe get started early on this, if at all possible. Next assignment is, if I remember right, has something with the first part is on using k-means clustering. So we talk a little bit about doing some clustering algorithms with k-means as an example, and then also the second half of the assignment is on using principal component analysis for dimensionality reduction. So I think the only thing I'll say today just about unsupervised learning. So both of these are examples of unsupervised learning when we're talking about these dimensionality reduction or these kinds of clustering techniques. These are all good things that you might want to know about for your project. So they can be useful on the data exploration. So for example, clustering can be useful if you have a data set, but you don't really have it already broken up into say different classes. You can sometimes discover the natural classes by applying a clustering algorithm, and after the fact decide that these belong to this class 1 and these class 2 and so on and so forth. So this is really kind of different from all the stuff we've done up to this point in the class. We've been concentrating on supervised learning, where you take a set of inputs, but they also have a label already applied to them. And so then you apply an algorithm like logistic regression or support vector classifier to learn a mapping from the input to the outputs. So that's really what supervised learning is. So for unsupervised learning, you don't have the labels. You have set data, but you don't necessarily have any labels. So you might use unsupervised learning, like I already mentioned, to begin to actually build some labels. You can maybe build some classes to turn into a classification problem, or just in general to learn some more about data. So dimensionality reduction can be very useful for learning more about the features that you have, or to recast your features into a different space that might be simpler or easier to model. I'll talk about all those, both of those a little bit next week. We'll probably start. Actually, I might start with clustering on Tuesday, and then talk a little bit about PCA on Thursday next week. So there are just in general clustering here. I'll leave it kind of as a last word, just the high level idea of what these are. So for clustering, like if you have the data, like the Irish data set, you might not necessarily know for some other data set, it might not already be labeled for you. So it would just be this, but you don't know what different classes you have in the data, right? So a common thing for clustering is to discover natural natural groupings, which you could think of as classes, so like binary or multiple classes in the data set. Right? So if you were had the iris data set, but you didn't know what each type of flower was, iris was that you had for each one of them, a good clustering algorithm might be able to naturally discover, right? So it's kind of easy to see that there's maybe two big clusters, the one Setosa and the others. It's maybe less obvious that this may or may not make a good breaking apart these into two or more separate clusters here. Our assignment, we use k-means, which is a easy clustering algorithm to understand. There's lots of other clustering algorithms. Our textbook covers has a whole section on a lot of others, and a lot of these are available in scikit-learn. But k-means is usually a good one to start with if you want to try and do some clustering on a set of data. And then real quickly, dimensionality reduction. So one way to think about dimensionality reduction is like this, and we can discuss why this could be useful. So here, this figure from the textbook is trying to represent we have data with three features, so it's three-dimensional. So this isn't exactly what PCA does, but so one way of reducing dimensions is just projecting, right? So I specify a two-dimensional plane, and then I project the three-dimensional features into 2 dimensions. So an easy way would be just to have a orthogonal straight line from the plane to each of the points in the original 3 dimensions to reduce it from 3 down to 2 dimensions. So there's lots of ways, lots of reasons why that can be helpful when you're doing data analysis, data exploration. So yeah, so that's, I think I'll go ahead, we'll stop there for today. Let me know. So don't forget about the assignment 6. If there's more questions, or if I didn't, I'll check on the one that was asked here. Make sure whether I was wrong or not about the randomness. But otherwise, yeah, do get in your assignment 6. Get your assignment 7s. I would encourage you to also get started with assignment 7s and get started with your last unit of materials here on supervised learning. So. All right. Yep, that's it. Let's go ahead and wrap it up here.